Hello students, in today's lecture we are going to find the location of all the 6 cardinal points of an optical system. In one of our earliest lectures, we discussed all the 6 cardinal points for an optical system. Now in this lecture we are going to discuss that we can represent all the position of all the cardinal points in terms of the elements of the system matrix. So first I have this diagram. Let me remind you. Here we have an optical system which has an input plane, and this one is the output plane. Let the refractive index here is n. Here the refractive index is n prime. Clear? Here this is the front focus point, which is at a distance p from the input plane, while it is at a distance f1 from the front principal plane. Here this dashed line represents the front principal plane, and this is the output plane. Here this line represents the back principal plane, while these points h1 and h2 they represents the principal point. This is the front principal point, while this one is the back principal points. However, this n1 and n2, these are the front and back nodal points respectively. Here the distances of the front focus point with respect to the input plane is p1, while with respect to the principal plane, the front principal plane, it is f1. Similarly, the principal point, the front principal point, is at a distance r with respect to the input plane, and the front nodal point is at a distance v with respect to the input plane. Similarly, for the back nodal points are the back cardinal points, this f2, it is at a distance f2 with respect to the back principal point, while this focus point is at a distance q with respect to the output plane, while the nodal points and the principal points, the back principal points, are at a distance omega and s with respect to the output plane. So all these cardinal points and their positions, we discussed them, I think, in our second lecture. So you must watch if you want to know more about them. Now we are going to find these distances, the relation for these distances, which is p, r, v, f1, and similarly s, omega, f2 and q with respect to the elements of the ray transfer matrix. Clear? Our object here in this is to derive the relationship between the distances which we defined for the cardinal points and the system matrix elements. So consider I have drawn these figures. Clear? Here for the front our input plane, this is the front principal plane, it is at a distance r, while the front focus point is at a distance f1 with respect to the principal plane, and it is at a distance p with respect to the input plane, and similarly this principal point is at a distance r with respect to the input plane. So we derived the we know that the matrix equation for an optical system, for any optical system, it is written as YF alpha F. These can be given in terms of the two matrices and their elements are, let's suppose, A, B, C, D. This is the matrix equation. This is the matrix for an optical system, and these are the linear equations. So this is Y naught alpha naught. That this is equation number 1. Or in equation form, we can write them as YF is equal to A Y naught plus B alpha naught. That this is equation number 1A. Clear? And for alpha F, we can write it as C Y naught plus D alpha naught. This is 1B. Clear? Now first we are going to find the distance, the position of the focus point with respect to the input plane. Clear? We are going to find P in terms of these elements A, B, C, D. Clear? Then we will going to find F1 and then R. So first we are going to calculate P, this distance in terms of the matrix elements. So here in this figure, let a point object is placed here at this point, which is at a distance P from the input plane, and a ray of light is coming toward the input plane. So when it reaches this point, it suffers refraction. So the angle of the incident ray with the optical axis is alpha 0, and after passing after entering to the optical system, there is no change in the angle here. There is no change. However, we know that the ray of light bends here, as we discussed in our position in the cardinal points. Clear? So therefore from this figure, that this is figure number A, figure A. This figure is available in the book which we are following. From figure A, clear? This is the figure. Here we see that when the ray at this point it refracts, so the angle of this ray, which is the refracted ray, with the optical axis is 0. Clear? When it reaches this point and it suffers refraction, so the angle of this ray with the optical axis is 0. So from figure A, alpha F is 0. So we can write this equation as 1B equation will become, this equation will become 0 equals to C Y naught plus D alpha naught, or Y naught C Y naught will be equal to minus D alpha naught, or Y naught will be equal to minus D over C into alpha naught. Clear? Or simply this will become, we can write it also as in this form, Y naught over alpha naught will be equal to minus D over C. That this is equation number 2. So for small angle approximation, if this angle is small, then the tan of this angle will be also equal to alpha. So for small angle approximations, this means that tan of alpha naught is almost equal to alpha naught. Clear? So the tan of alpha naught will be equal to this distance is y naught. Clear? At this point the height or the altitude of the incident ray is y naught. This is y naught upon phi. So alpha naught is equal to y naught upon p. But however, we know that all the distances directed towards the left are taken negative, while the distances directed towards the right are taken positive. So this distance, as you see from in the figure, with respect to the input plane, this distance is directed towards the left, so therefore this will be taken negative. So this is minus p actually. So this implies that p will be equal to minus y naught over alpha naught. Clear? But we know that y naught over alpha naught is equal to minus d upon c. Therefore p will be equal to d over c. This is equation number 3. So this is the position of the front focus point with respect to the input plane, and that is determined by the DC elements, the ratio of the DC elements. Clear? Whenever we are going to calculate the front focus point of any optical system with respect to the input plane, that will be the ratio of these two elements. Similarly, now we are going to calculate f1. Similarly, here in this figure, look here. Again, for small angle approximations, this alpha naught will be equal to yf, because this distance, this height is yf over f1. Similarly, from figure A, alpha naught for, but remember that this we are going to calculate it for small angle approximations. Alpha naught will be equal to yf divided by f1, but again this f1 is directed towards the left, so it will be minus f. And thus from this equation, f1 will be equal to minus yf upon alpha naught, and this will be equal to yf here from this equation, this is, which is from equation number 1b. Sorry, 1a. This is yf. Yf is ay naught plus b alpha naught. Therefore, using equation number 1a, it will be minus a y naught plus b alpha naught divided by alpha naught. Clear? Or this will be equal to minus ay naught over alpha naught minus b, because this alpha and alpha will be cancelled, and y naught over alpha naught, which we calculated in equation number equation number 2. y naught over alpha naught is minus d over c. So by using equation number second, by using equation second, this f1 will be equal to this negative sign, and negative sign will become positive, so it will be a d upon c minus b, or we can write it as ad minus bc upon c, and this is actually ad minus bc is the determinant of the matrix M over C. Clear? Our F1 is equal to, yesterday in our previous lecture we found that determinant of M is always equal to the ratio of the initial and final media. Clear? Therefore this will be N naught over NF times 1 over C. Now this is equation number 4. So this is the position of the focus point or the focal length, which is measured with respect to the principal plane. Clear? And it is it depends on the ratio of the initial and final media, and also it depends on the C matrix element. It depends on this. Now this R, we are calculating this R. So here from this figure, again to calculate, now to calculate position of principal point or principal plane, which is with respect to input plane, because this distance is measured with respect to the input plane. So here in this figure, by using the convention that the distance directed towards the left are measured negative, will be taken negative, while the distances directed towards the right are taken positive. So here we see that this is minus f1, there minus f1 is equal to r minus p. Clear? So this is, or I can write it as r minus p is equal to minus f1. Clear? This is r is taken because the magnitude of r and p is equal to f1. This is clear, but I have written negative sign with p. This is because this distance is directed towards the left, and also I have written negative sign with f1 because that is also directed towards the left. Therefore r will be equal to p, because when it is brought to the right it will become positive, p minus f1. And now we have calculated p distance and f1 distance. So substitute those equations, which is equation number 3rd and 4th. This is p and this is f1. Clear? So by putting equation number 3rd and fourth. So we get that R will be equal to P, which is D upon C, minus F1, which is N0 over NF into 1 over C. R, we can write it as 1 over C times D minus N0 over NF. So this is the R, which is 1 upon C into D minus N0 over NF. So this is equation number 5. So these three cardinal points, the front cardinal points, are calculated. Now we are going to calculate the back three cardinal points. So for the back cardinal points, which is for the back cardinal points, therefore consider now the figure B. This is figure B. Because at the back side of the optical system the rays emerges. Clear? I hope you can see it. Here this is the input plane, this is the output plane, this is the back principal plane, this is the back principal point H2, this is the focus point, back focus point. It is at a distance q with respect to the output plane, while it is at a distance f2 with respect to the back principal plane, and this principal plane is at a distance s with respect to the output plane. Clear? So when a ray of light, as we see here, it was inside the optical system, it is going parallel. So a parallel ray inside the optical system is traveling. So when it emerges the back principal plane, so it focuses towards the focus point. Clear? So initially the angle of this ray with the optical axis was 0. Here alpha naught, which is the angle of this ray with the optical axis, is 0, and when it emerges, its angle with respect to the optical axis becomes minus alpha f. The negative sign is taken because this angle is below the optical axis, because the angle is taken below the optical axis. The angle of the ray with the optical axis is below. Therefore, for the back cardinal points, consider figure B, which is this one. So from this figure, YF is equal to A y naught plus B alpha naught. This is equation number 1a. Clear? This is the matrix equation. YF equals to A y naught plus B alpha naught. These are our primary equations. Since I told you that alpha naught is 0, the angle of this ray with the optical axis is 0. Since alpha naught is equal to 0, so YF will be equal to A y naught, or YF over y naught will be equal to A. Here yf. This is the primary equation for the optical system. Yf equals to a y naught plus b alpha naught. But here in this figure, y alpha naught is equal to 0, so this equation will become yf equals to a y naught, or yf over alpha naught will be equal to a. Let this is equation number 6. And from the second equation, which is this one, 1b, alpha f equals to cy naught plus d alpha naught. Also from equation 1b, which is alpha f equals to cy naught plus d alpha naught. But here alpha naught is 0, therefore it will become alpha f equals to cy naught. Clear? Or c will become equal to alpha f over y naught. Clear? And alpha f from this figure, alpha f for small angle approximation, alpha f will be equal to yf over this distance is yf divided by q. Clear? So this will be c will be equal to minus yf over q y naught. Clear? I will write it here that from figure 2, from figure B, alpha f is equal to alpha f, and this is negative, this distance, this angle is negative, so I have written this negative sign comes here. Alpha f is equal to yf over q. But here you see that this angle is below the optical axis, therefore this angle is taken negative. Clear? And in equation number 6, yf over y naught is a. Therefore by equation 6, c will become equal to minus a over q, or q will be equal to minus a over c. This is equation number 7. So this is the position of focus point, back focus point with respect to the output plane. Now f2, we are going to calculate this focal length, which is the distance from the back principal plane to the focus point. So similarly, again from figure B, this alpha f, but I have written negative because this is negative. This is also equal to, this is equal to the ratio of these two. This is y naught, this distance is y naught from here to this one, divided by f2, y naught divided by f2. Clear? Or f2 will be equal to minus y naught divided by alpha f. Clear? And this can be written further as alpha f is cy naught here in this equation which we have calculated. Alpha f here we have calculated this one here. Alpha f is cy naught, therefore this will be equal to minus y naught divided by alpha f will be c y naught. So y naught will be cancelled and we will get f2 equals to minus 1 upon c. Clear? This is equation number 8. So this is the position of f2 with respect to the back principal plane, and this is given in terms of the element of the matrix, system matrix. Now we are left with S. We are going to calculate S now. So again from that figure, from figure 2, from figure B, this f2 is equal to q minus s, because s is directed toward the left, therefore I have taken it negative. Or s will be equal to q minus f2, but we have calculated q and f2 as well. Q is this equation, which is equation 7, and f2 is equation number 8. So put equation number 7 and 8 in this equation. This is q, this is f2. So by equation 7 and 8, s will be equal to q is minus a upon c minus f2. So this negative signs will become positive, and this is 1 upon c. Or this will be equal to 1 upon c minus a upon c. Or s will be equal to 1 minus a upon c. This is equation number 9. So we have calculated the position of the back 3 cardinal points. Now we are going to calculate the nodal points, the front nodal point and back nodal point. For nodal points, consider figure C. So this is figure C now. This is the input plane, this is the output plane. When a ray of light strikes the input plane at some angle with the optical axis, so it doesn't go straight. So one refraction occurs here and second reflection occurs here at this point. So these 2 points are called the nodal points. This nodal point with respect to the incident plane is at a distance v, while the back nodal point N2 is at a distance omega with respect to the output plane. So now we are going to calculate these positions, the position of n1 and n2, which is v and omega. So again, for small angle approximations, from this figure, alpha, this alpha is equal to y naught over v. This distance is directed towards the right, so it is positive, while this distance, this negative sign, this is directed below the optical axis, because the incident ray intersects the input plane below the axis. So this alpha will be equal to minus y naught over v. Clear? Here the negative sign with y naught indicates that the ray intersects the input plane below the axis. Also the input and output rays makes the same angle relative to the axis. Here the angle of the incident ray with the optical axis of the input and output is same. Clear? This angle here, you can consider it here or here. So the angle of the output and input with the optical axis is same. Therefore, so the output angle and the input angles are same. So let me write it first, that y naught, I can write it as y naught over alpha can be equal to minus v. Let this is equation number 10. Since the angle of the input ray and output ray with the optical axis is same, so from figure alpha naught is equal to alpha f, and I have mentioned them by alpha. So from equation 1b, which is this equation, this will become alpha, this will become alpha. So from equation number 1b, alpha will be equal to c y naught plus d alpha, or I can write it as y naught over alpha is equal to 1 minus d divided by c. Clear? Bring this term towards the left, it will be minus d over alpha, and then take alpha common from those two terms and bring it to denominator with y naught. So you will get this equation. So this is equation number 11. So from equation number 10 and 11 we see that from 10 and 11, this is minus v is equal to 1 minus d over c, or v will be equal to d minus 1 over c. Let this is equation number 12. So this is the position of the front nodal point, the position of the front nodal point. This is v, which is given in terms of the matrix elements d and c. So for the back nodal point omega, similarly for omega, again consider this figure. Here alpha will be equal to yf over omega, but here omega is directed toward the left, so it will be taken negative. So alpha again is yf over omega, but this negative sign here is because the omega is directed toward the left. Or omega will be equal to minus yf over alpha. This is equation number 13. And again from equation number 1a, again from equation 1a, which is our primary equation, which is yf is equal to a y naught plus b alpha naught, but alpha naught here is alpha. Therefore, substitute this value in equation number 13. Therefore, 13 will become omega is equal to minus a y naught minus b alpha divided by alpha, or this will be equal to minus a y naught over alpha plus b, sorry, this is minus b, or y naught over alpha, which is from equation number 11, y naught over alpha, this is 1 minus d over c, 1 minus d over c. So I can write it as omega is equal to minus a times y naught over alpha, which is 1 minus d upon c, 1 minus d upon c minus b. Clear? Or I can write it as minus a minus ad over c minus b, or further I can write it as minus a minus ad minus bc over c. Clear? And here this is positive, this term is positive. When a is multiplied with 1, it is minus a, and this will become positive. Clear? These two terms are positive. But in our matrix, which is of the form, the matrix is of the form A, B, C, D. The system matrix is of this form. I can write it as minus A into plus AD minus BC over C. Here you can see that AD minus BC is nothing but it is the determinant of this matrix. So I can write it as minus A plus determinant of M divided by C. And we know that determinant of M is equal to the ratio of the initial and final media. This is omega is now minus A plus N naught divided by NF divided by C. So this is equation number 14. So this is the Back cardinal point. So we have calculated the position of all the cardinal points in terms of the elements of the system matrix. Now here are special cases of the position of the front focus point with respect to the input plane and output plane, which is P and Q respectively, and similarly for F1 and F2, R and S. So we consider here that the front media and back media of the optical system are different, having refractive indices N0 and NF. However, if these two medias are the same, if N0 is equal to NF, or we assume that both the mediums are air, then N0 and NF will become 1. So in that case, the principal point and nodal points coincides, that is R will become V and S will become omega. Let me write here that when, this is the first case, when N0 and NF they become equal, clear, then R will be equal to V and S will be equal to omega. This means that this principal plane and the input plane, the principal plane and nodal point, the principal point and nodal point will coincide. This means that principal points and nodal points will coincide. Clear? Also the first and second focal lengths of the optical system will become equal in magnitude, and you can see them from these equations which we calculated, F1 and which is F2. These are the two equations. Here if N0 will become equal to NF, then F1 will be left with 1 over C and F2 will be equal to, here it will become minus 1 over C. So if the front and back media of the optical system becomes the same, then F1 and F2 will be equal in magnitude. Second, F1 and F2 will be equal in magnitude. Third, the separation of the principal point is the same as the separation of the nodal points. That is, this means that R minus S will be equal to V minus omega. This is the separation of the principal points of the front and back, and this is the separation of the nodal points of the front and back respectively. So these separations will also become equal. So I hope you will understand our today's lecture. So thank you very much.